Okay, in this video I'm going to talk about the connection between the chromatic number of a graph and the minimum degrees of its subgraphs. So let's recall the definitions. So the chromatic number of a graph, it's denoted as chi of g, so it's chromatic number like it's defined as the minimum number of colors required to color the graph properly. Required to color the graph G properly, and proper coloring is a coloring where any two adjacent vertices receive different colors. So like if this is the same color and they are connected by an edge, so this is prohibited. So any two vertices that are connected by an edge must get different colors. So, and the minimum degree of a graph is called, like we denote it as delta of G. Delta of G, so this is the minimum degree, and it is defined as the minimum of all degrees of vertices, degree of vertex V for all vertices V in the graph G. So yes, here we can write V belonging to the set of vertices of G. So the main theorem that I'm going to prove is that theorem so for every graph G there is a subgraph H, subgraph of G, such that the following properties hold. So the chromatic number of H is the same as the chromatic number of G, and the minimum degree of H is greater or equal than the chromatic number of G minus 1. So we can find a subgraph in any graph with the same chromatic number as the original graph and the minimum degree bounded from below in terms of the chromatic number. So let's prove this. So we are going to remove the vertices of G, preserving the chromatic number. So let's write remove. So like if there is a vertex, so if G has a vertex has a vertex now let's write so let's write so we remove the vertices of G, preserving like one by one, preserving the chromatic number, until we can. Well, while we can, like while we can. So if there is a vertex in G that removing which keeps the chromatic number, so it doesn't decrease the chromatic number, then we remove this vertex. If like in the remaining subgraph, if there is still a vertex like removing which the chromatic number would be the same, we remove this vertex. So we continue this until we can. Clearly there would be a moment when we need to stop, because well, if we remove all vertices, like if one vertex remains in a graph, like it clearly has a chromatic number less than the original, well, unless it was one colorable, like in which case it's in which case it's a graph without, like empty graph without any edges. Yeah, so like the empty graph without any edges, we can consider it separately. So like for this graph, this theorem clearly is true, because well, the minimum degree is 0 and the chromatic number is 1. So for any subgraph, so this actually holds for any subgraph. So of course there is a subgraph. So if the graph is not empty, then it has at least a single edge. Graph has at least a single edge. Therefore the chromatic number is at least 2. The chromatic number of G is at least 2. Because we need two separate colors for the ends of this edge, and so when we remove all vertices, when we have a single vertex remaining, it has a chromatic number 1. So it's clear. So when like during this removal of vertices, when we go from the whole graph G to a single vertex, at some point we would decrease the chromatic number, right? And so this proves that we need to stop at some point. So there would be a moment when we would need to stop before we reach a single vertex graph. So let's write this. So like at some point, we would no longer be able to remove this vertex. We would stop. No longer being able to remove the vertex, preserving the chromatic number. So this means that so take this as a subgraph. take this like remaining subgraph as the desired subgraph H. Subgraph H. So so denoted by H, the remaining subgraph after the removal of these vertices, denoted by H. So now this subgraph H so it has the properties so that the removal of any vertex, now the removal of any vertex of H, it's important that of any vertex, not just of some vertex, but of any vertex. So the removal of any vertex of H strictly decreases its chromatic number. Well, this is because if removing some vertex doesn't decrease its chromatic number, then we continue the previous process of removal of vertices. So the H is defined as the subgraph that obtained by removal of this procedure of removal, where we cannot proceed any further. We cannot proceed any further means that the removal of any vertex further now decreases the chromatic number of G. So, but this means that so like now I claim that so we take it as the desired subgraph H. So the chromatic number, so this property is true by construction, because we constructed the H by removing the vertices, preserving the chromatic number from the original graph G. So the He of so the fact that the He of H is the same as the He of G, this is trivial by construction. By construction. Now we need to prove the second property, that the minimum degree of this subgraph would be bounded from below by the chromatic number. So let's say that this is not true. So we need to prove that so we need to prove that delta of H is greater or equal than He of G minus 1. He of G or He of H, it's the same thing. So suppose it's not true. Suppose not true. This means that delta of H is less or equal than He of G, right? no, not he of g, but he of g minus 2. Yeah, so like let's write it more carefully. So it's strictly inverting this inequality. So it's strictly less. So not true. Greater or equal is not true. It means that it's strictly less than he of g minus 1, and therefore it is less or equal than he of g minus 2. So if it, because it's an integer number, so if an integer number is strictly less than another integer number, then it means that it's less or equal than this number minus 1. So from this we need to subtract one more, like minus 1 from this, take minus 1 from this. So we get it's less or equal than he of g minus 2. So this means that so this means that there exists a vertex v in H with the degree well, I don't have a place here, enough space here. So this implies that there exists a vertex v in H with the degree less or equal than this number he of g minus 2, because this is delta of H is the minimum degree, so the minimum among all degrees of all vertices in H. So it means, by definition, it means that there is a vertex the degree of which is less or equal than this. So let's say that this is vertex v. So this is the subgraph H. Right. So remove this vertex v. So now we remove this vertex v. Remove v. So the resulting subgraph, so let's denote it H prime. H prime is basically like H minus vertex v with the removed vertex v. So this subgraph, so by the previous property that we established, so the removal, this property, the removal of any vertex of H decreases its chromatic number. So the chromatic number now of H prime would be strictly less than the chromatic number of H, which is the same as the chromatic number of G. So if it's strictly less, then when we add back this, so let's say that we could take a coloring of H prime with this number of colors. When we add back this vertex v, it has no more than so the degree the degree of vertex v in H. So it's not like, it might be confusing. It's not the degree in the original graph, but the degree in H. So the degree with index H is less or equal than this. So less or equal than he minus 2. So we have at most, so this vertex v has at most he minus 2 neighbors. At most he minus 2 adjacent vertices in H. So if the chromatic number is strictly less than he of g, then we can color H prime in he of g minus 1 colors. It might be that we need even less colors, but at least at most in this number of colors we can color. So it is colorable in this colorable properly in this number of colors. Therefore, when we add back this vertex v, it has, so this vertex v, in H, it has no more than he of g minus 2 neighbors. So, and whatever colors they receive in this coloring, like there is in this coloring in he minus 1 colors, like these vertices neighbors of v take take at most he minus 2 colors. So the neighbors, because there are he minus 2 vertices, so the neighbors of v take less or equal than he of g minus 2 colors, because there are less or equal than he minus 2 vertices in total. So each of them takes at most one color. So we can always, so there is one color remaining. So in the coloring in he minus 1 colors, there is one color remaining. There is at least one color remaining, like in the total number of colors, and we color v with this color. So color v with this color, and so basically we would get a coloring. We get a coloring of H now in he of g minus 1 colors. So we effectively extended the coloring. So we take the coloring of H prime in this number of colors, and we extended it to H. So because V has the degree less than he minus 2, we can always extend. So we effectively extended. So we extended the the coloring from H prime to H, the coloring in this number of colors. So this means that the chromatic number of H is also less or equal than E of G minus 1, because we extended the coloring from H prime to H, and now we have a coloring of the graph H in this number of colors. So the chromatic number is the minimum number of colors required to color, and we showed the coloring in this number of colors. So the chromatic number is less or equal than this, but this is a contradiction, because the contradiction with this, because the chromatic number of H was exactly equal to chromatic number of G. So this is equal to chromatic number of G. This is a contradiction. Yeah, a contradiction with the assumption, with this, we suppose that it is not true. Yeah, so this assumption generated a contradiction, led to a contradiction. Therefore, this is true. So a contradiction that implies that delta of H is greater or equal than E of G minus 1. Yeah, and this concludes the proof of the theorem. And so now there is a corollary of the theorem. So let's write it as another theorem. And that says that the chromatic number of G can be bounded from above by this number, maximum of the minimum degree of all subgraphs, maximum among all subgraphs of G. So among, like, we take the maximum among all subgraphs H of G and the maximum of the minimum degrees. Plus 1, excuse me, here is plus 1 also. Maximum of this plus 1. And so this follows from the previous theorem. Yeah, so there is a subgraph. So by so from this inequality we get that E of G, like the other way to rewrite this inequality, so by the previous theorem, theorem, there exists a subgraph H of G with the properties that he of H is the same as he of G, and the minimum degree of the minimum degree of H is greater or equal than he of G minus 1. So we actually don't even need this property, so we can forget about this. The only thing we need is that the minimum degree, so like there is a subgraph with the minimum degree less with the minimum degree greater or equal than this. So this can be rewritten as he of G of G greater or equal than delta of H plus 1, right? And now we simply take the so there exists a subgraph H, subgraph H with this property. So if you take the maximum among all subgraphs H, excuse me, here should be less or equal. So the left, like yeah, so the left hand side of this inequality doesn't depend on H. So when we take, so there exists a subgraph H with this property that he of G is less or equal than this. Then when we take the maximum among all subgraphs, this number would be could be the same or greater. So the maximum. So let's denote it. So not to confuse with this H used in this maximum. Let's denote this subgraph as H0. H0, H0, H0. Right? So there exists this subgraph H0. So then we can write that the maximum of delta of H for all among all subgraphs of G is greater or equal than this value for a specific subgraph, right? The maximum for all subgraphs is greater or equal than this value for a specific subgraph. Then for this subgraph H0, and for this subgraph H0, we found that. Well, we found from this, right, that it's greater or equal than he of G minus 1. And from this it follows, now we look at the beginning and at the end. From this it implies immediately that he of G is less or equal than maximum delta of H plus 1. Yeah, this is exactly what we needed to prove. So this concludes the proof. So this is effectively a upper bound on the chromatic number in terms of the minimum degrees of the subgraphs, not on a single graph, not on the whole graph, but the minimum degrees of like among all subgraphs of G. So if you know this, like all these minimum degrees of all subgraphs, then we can estimate, then we can bound from above the chromatic number of G. Yeah, so that's it for this video.